Okay, so let's start talking about these. So if we want to figure out which neural nets can draw this picture, what do we need to know first? What might we ask first? How do you draw a picture with a neural net? What does the first layer of a neural net do?
Draws lines.
Yeah, so the first layer is going to draw lines. So like in this one, we'll draw 2 lines, and this one will draw 3 lines. And what do the remaining layers do? Yeah, they combine it with logic function. They combine the line shadings with logic functions. So the first question we want to ask is how many lines do we need to draw? So for this one, how many lines would we need to draw? 2. So we could have a line like that, another line there. And then we have to decide which side of each line to shade. So which side should we shade in this case?
Top side.
Top side? Yeah, that would work. There isn't really a right or wrong answer for which side to shade. You might just have to negate things if you choose to shade the other side. So then what logic function could we use to combine those shadings to get the top shaded area? OR. So this is an OR function. So we could do this with 2 neurons that each take in x and y inputs. So there's our 2 lines. How many neurons do we need to draw an OR? See different numbers. So if we wanted to figure it out again, we could go back to our truth table where we have x, y, or x and y are each either 0 or 1. OR is going to be true whenever x is true or y is true or both, so that'll be 0, 1, 1, 1. And then if we graph that, and we color in all of the points that have a value of 1, we would get these 3 shaded. And so then you can see how many lines would we need to draw an OR function. Just 1, yeah. So we could draw an OR function like that by shading that side of that line. And that could be something like, let's see, x, y, would give them both weights of 1 and a threshold of 0.5. That would be an OR function. Yeah.
What's the line that you said that you drew there?
This line?
Yeah.
Yeah, so in this case, this would be the line
Y equals minus x.
y is greater than or equal to negative x plus 0.5. So there are many possible lines you could draw. So there are many ways you could draw an OR neuron. But in this case, here's one way of making an OR using a single neuron. So we can combine these using our OR. So which of the neural nets can do that? A, because that's exactly what we just drew here. A works. Does B work? Yeah, we can just ignore, it just has an extra neuron. We can just ignore that by giving it weights of 0 or something. So extra neurons are fine. C doesn't work because it doesn't have enough neurons. It only draws a single line. What about D? Yeah, it just has extra neurons, so we could just pass the things forward through the neural net. So A, B, and D for that one. For the second one, how many lines do we need to make this shape? Common answers are 1 or infinity, which are rather different. So the thing is, lines have to be straight. And this is a curvy shape, so we can't actually do this with 1 line. We would need infinitely many lines that go like this. But we could never actually make that curvy shape because it would always be some sort of polygon. So we can't do this with any of our neural nets. We'll come back to this one at the end because it's a bit trickier. So how about this fourth one? How many lines? 2 lines. So we have a vertical line and a horizontal line. We might shade, say, the right side of this one and the underside of that one. What logic function would we use to combine those? XOR, yeah. Can we make an XOR function using 1 neuron? No, how many do we need? Well, we could figure that out. So let's call these lines A and B, and put this over here. We have A, B, and the XOR of A and B. These can each be 0 or 1. XOR is going to be true when A is true or B is true, but not both. So we have 0, 1, 1, 0. And if we graph that, we get the point at 0, 1 shaded and 1, 0 shaded. So how many lines would we need to make an XOR? 2 lines. So we could do something like those 2 lines, but then we could combine them using a simple logic function. Like we could shade them both toward the middle and combine them with an AND. So to make our XOR, we would have our inputs that we call A and B in this case, going into the 2 neurons that draw these 2 green lines, and then we would combine those with an AND. So if this is an XOR, and we said we needed 2 lines here, how many neurons do we need in total? So if we draw this neural net, we have our inputs X and Y going into neurons A and B, and then we need an XOR. So how many neurons in total? Yeah, 5. Because our XOR looks like this. One question we can ask though is, do we actually need all of these wires going into A and B? Does line A care about both X and Y? No, it only cares about Y because it's a perfectly horizontal line. So A could just have the input from Y, and B can just have the input from X, and that makes the neural net slightly simpler. I guess we could untangle this by doing, we relabel them B and A, and it looks cleaner. So which neural nets can do that?
D.
Only D, yeah. Because D is basically the structure, but with the extra wires. B can draw 3 lines, but that doesn't help us because B can't do an XOR function with this 1 second layer neuron. And A and C just don't have enough neurons. Okay, so then what about this one? How many lines do we need to draw? Just 1. And in this case, it's a horizontal line, so we only care about Y as an input to that neuron. So that's actually even simpler than neural net C. So can all of these draw it?
Yes.
Yeah. So we have A, B, C, and D. What about here? 3 lines. So we could label those lines, we could call them A, B, C. What sort of logic function might we want to use to combine those to get that picture?
And
Yeah, so and, well, do we want to AND them all together? Say we shade toward the shaded region on all of them. What would we get if we did the AND of A, B, and C, all ANDed
C.
together?
C.
We would only get this little region up here.
That's and or.
Yeah, so we want an and an or. So we could combine A and B with an and. So we have A and B combined with a 1 neuron that does an and. And then we can OR that with C because C gives us the whole top region. So if we're in the AB region or if we're in the C region, then we get a shaded region in the end. Can any of our neural nets do that? Oh, we're missing inputs X and Y. It looks like C only needs Y and A and B only need X, so we get that. Can any of our neural nets do that? So only B can draw 3 lines. But how many neurons do we have here after the first layer? 2. We have this and this or. So this particular neural net, none of our neural nets can do. But maybe we can find a simpler way to draw the same picture. So one trick we can use is to think about, in each of the 6 regions defined by these lines, how many lines were on the shaded side of. So for example, over here, we're not on the shaded side of C because the shaded side of C is above. We're not on the shaded side of A, but we are on the shaded side of B because B is shading to the left. So we're on the shaded side of one line there. How about in this section? 2, because we're on the shaded side of A and the shaded side of B. Here we're only on the shaded side of A. Here we're on the shaded side of C and B. Similarly over here, A and C. And then what about this one? All 3 of them. So now we can see what do all the shaded regions have in common numerically.
Or at least 2.
Yeah, they're all at least 2. So that means that what we can do here is we can use a trick where we just look at these numbers. And we can say we have our 3 neurons, A, B, and C, that draw the 3 lines. And we want to, let's say we give them all weights of 1, and then put them into some neuron. What threshold might we want for this neuron?
1.5.
Yeah, we could try 1.5. So that way, whenever we're on the shaded side of at least 2 of these lines, it'll produce a 1. And whenever we're on the shaded side of only 1 line, then it'll produce a 0. So this neural net is a simpler way of performing the same logic as that in this case. And then again, we would have our inputs x and y. So now which of these neural nets can draw this picture? Yeah, now B works, because we found a way to do it with only 1 second layer neuron. But we still can't use A, C, or D because they don't draw enough lines. So let's see about this one. This one, it looks like we also need 3 lines. So we could, it looks like a similar situation where we'd have an AND area here. We label these lines A and B, that's the AND of A and B. Or we could be in the C region. So we could do this AND OR thing again. Will this work again? We could check by putting numbers in the region. So here we're on the shaded side of A only, here we're on the shaded side of A and B. Here B only, and here B and C. So that'll work again with this threshold of 1.5. So which neural nets can draw that picture?
B.
B. What would we have to change from this neural net to draw this picture? What's different? Something about the wiring.
They're all Ys.
Yeah, here we would want all of them to be Y going in, whereas over here, so for this only worked for this one. For this guy, we would need Y going into A, B, and C, and then so on. Okay, then what about this picture? How many lines do we need?
2.
2. And what kind of function might we use to combine them?
And
And. So if we have 2 lines, we combine them with an and. It looks like one of these only needs x input and the other one only needs y. Which neural nets can do that?
A, B, D.
A, B, and D. Because they're all at least as complicated as this. So now we can go back to this one that we skipped. How many lines do we need to draw it? 3. So we have this horizontal line, we will shade under it, and then we have these 2 diagonal lines. So we could say shade to the right of both of them. What does this shape look like, logic function-wise?
Excellent.
Yeah, we're probably going to need some kind of XOR in here. So we could do some complicated thing where we combine an XOR and an AND, But in this case, it looks like the only neural net that can draw 3 lines is B, and it can't do an XOR with that one neuron. So in this case, the answer is just going to be none because B isn't sufficiently complicated to do an XOR. Are there any questions on this? Okay, so now on the other side of the page, let's do this problem. There are handouts over there if you didn't get them. So this one, we're trying to draw a specific shape. So what might we want to do first? Yeah, find the equations of the line. So what are some of the equations? Just shout out an equation if you find one.
X plus y is equal to 3.
X plus y is equal to 3, so that's this guy. We'll color code them. Do we want this to be less than 3 or greater than 3?
Less than.
If we do less than or equal to 3, then it'll shade toward this shaded region. So that looks good. Less than or equal to 3. And if we reformat this equation to look like ax plus by is greater than or equal to t, which is our standard neural net equation, then we would get something like negative 1x minus 1y is greater than or equal to negative 3. So what's another line?
X equals y.
X equals y. So that's this one. We want x is greater than or x is less than y. Which side should we shade?
Less than.
Less than? So what would less than do?
It would shade to the left and above.
Would it? So we could test a point, like say the point 0, 4, and see if we put in x is 0 and y is 4. Oh, I guess that's, oh, you're right, okay. Good. Okay, so that shades this way. And so if we rearrange that equation, then we would have 1y minus 1x plus 1y is greater than or equal to 0. And then what's the last equation? Yeah, x plus y is greater than 5. That's this one, and we're shading above it. If we rearrange that, we get 1x plus 1y greater than or equal to 5. So now we can start trying to fill in those equations on this neural net. So which one, so we're given some numbers on this neural net already. Do any of the numbers in the neural net match the numbers in the equations? Yeah, the 5 and the negative 3. So we could put this 5 equation over here, b can be the pink line. And we would get weights of 1 and 1 and a threshold of 5. What's going on with the negative 1 here? Does that mean we should negate something? So that's just saying that we move the threshold to the other side of the equation. So this equation is equivalent to ax plus by plus negative 1 times t is greater than or equal to 0. So if we treat the threshold as a weight, then we have a negative 1 there. Okay, so then we said the negative 3 looks like this blue line. So what would be the weights going into D?
Negative 1 and
-1 and -1. And so then hopefully A is the green line. Looks like we have a weight of 1 for y, so that matches -1 for x, and threshold of 0. Okay, so now we have to figure out how to combine these line shadings just like we did with the pictures. So what sort of function might we use to combine them? Yeah.
Oh, like the pink and yellow, or like the blue one. If we were like
Yeah, exactly. Yeah, here let's label these, that'll make it easier. So B, A, and D based on the way we match them to the neural net. So we just said B and D. Or no, B and A, B and A. Or D. Okay, so now we just have to see if we can perform this logic using our remaining 2 neurons. So what would we want C to do? To do A and B. So if we want C to be an AND, specifically this AND would be C. We're given weights of 2 for A and 2 for B. So we know that these outputs can each be either 0 or 1. So going into C, we have either 0 or 2 and 0 or 2. And we want C to produce a 1 only when both of those are true. So what threshold might we use?
4 or 3.5 or something?
Yeah, 4, 3.5, those would work, or 3. So I think the problem specifically said is use computers, so we could use 3 or 4. So with that threshold, we would have whenever only one of them is true, it'll produce false because it's less than 3, and if both of them are true, then it produces true. So now we have C is computing an AND function. And so then what do we want E to do?
An OR?
Yeah, OR. So E will be this OR. So we're given a weight of 2 and a threshold of 1. What weight might we want over here?
At least 1.
At least 1? So let's see if that works. So if we have an output of 0 for either of these, then we'll have, so if C is 0 and D is 1, then we'll have a 1 going in, and that is at least as large as this threshold, so it would produce a 1. If they're both false, then we have 0 going in, and it's less than the threshold, and if they're both true, we get a 1 out, so that's good. So now we have a neural net that produces this picture. And if we wanted to write an equation for the output, there are many ways we could do it. We could say the output of E is going to be 1 if this thing is true and 0 otherwise. We could also say the output of E is 1 if, say, 2 times C plus this 1 times D is greater than or equal to that threshold 1 and 0 otherwise. And we could also take that more levels up the neural net by combining the previous neurons into this equation. Are there any questions on this? Okay, so now we can either do more neural nets or go on to SVMs. Who wants to do more neural nets? Who wants to do SVMs? Okay, let's do that. Okay, so there's a page that has 2 small pictures on it. Let's start with that one. It's from 2015 from student. support vectors do we have? 3? Yeah, so we have D, B, and C are all support vectors. There are a couple of ways we could figure that out. One is if we removed any one of those points, the boundary would change. If we removed B, the boundary would be over here. If we removed C, the boundary would swing up just a little bit. And if we removed D, there would be no negative points at all, so everything would just be positive, and we wouldn't even need the boundary. Another way we could figure it out is the convex hull method, where we pretend that we're stretching a rubber band around all the positive points and around all the negative points, which in this case is just D, so that's kind of silly. And then that makes it easy to see that the closest point in this convex shape to the point D is somewhere along this line. So we have a line and a point, which means that our boundary will be parallel to that line. So if we didn't have the boundary drawn, that's how we could figure out where it is. So there's our boundary and our gutters, and we have 3 support vectors. Now we're asked to figure out the supportiveness or alpha values for each of these points. So how would we go about doing that? In this case, we only need to know the sign of them. So how would we figure out the sign of the points? Yeah.
If it's a support vector, it's going to have a positive alpha.
Yeah, exactly. So if it's a support vector, then it'll have a positive alpha. What if it's not a support vector?
0.
0, yeah. So what's the alpha value for point A?
0.
0, because it's not a support vector. And then these guys will all be positive. If we did want to calculate the alpha values, or if we wanted to compare them in more detail, some things we could notice are the sum of alpha B and alpha C is going to be equal to alpha D. Alpha B plus alpha C. And that comes from something we called equation 4 last time, where basically the sum of the positive alphas equals the sum of the negative alphas. So that tells us that alpha B and alpha C are each less than alpha D. We could also compare alpha B to alpha C. So which one of those would be smaller?
C.
C. So the reason why we know that is we can imagine removing each one and see how much the boundary would change. If we remove B, the boundary changes a lot to there. If we remove C, it only moves a little bit. So that means that B is playing a greater role in determining the boundary. So we have alpha B is greater than alpha C. Okay, and then we're asked to classify this unknown point E. So how would we classify that?
Negative.
Yeah, negative, because it's on the negative side of the boundary. So if we wanted to do it mathematically, the rule would be the classification of point E is a sine of W dotted with coordinates of E plus B, which if we were to calculate W and B, we would find that this is a negative value. We can also just look at the picture and see that it's on the negative side of the boundary, and anything there is going to be negative. Okay, so then we're told, let's say that point C is moved. So now instead of being over here, point C moves to there. So how does that change our support vectors? Do we still have 3 support vectors?
I only need 2.
Yes, and now we only need 2. So we definitely need D, because it's the only negative point. Do we want D or C?
C.
C. And so we can figure that out the same way we figured it out before. One is if we removed B, the boundary wouldn't change, or actually if we removed C, it would change. Another thing is we could draw our convex hull again. We stretch a rubber band around the points. And we would see that the closest point in this triangle to the point D is that corner where C is. So our boundary is the perpendicular bisector of C and D. So then we want to figure out how all of these alpha values changed. So how did the supportiveness of A change? No change, because it's still not a support vector. So alpha A, no change. what about the supportiveness of B? We said that now it's not a support vector.
So decreased.
Yeah, so it's going to decrease. And now it's going to be 0 because it's not a support vector. And then what about point C? First we could ask, what about point D? Does it have any reason to change? No. So point D has no change. And now our equation becomes alpha C equals alpha D. So how did alpha C change?
Increased.
It increased. And that makes sense because previously B and C were sharing the job of defining the positive gutter, whereas now C is doing all of the work itself, so it makes sense that it would have a higher supportiveness now. And then finally we're asked, how would we classify point E? Has that changed? No, it's still negative. Okay, so now let's do the problem on the other side with the one-dimensional SVM, and we'll actually calculate some of these quantities. So what shape is the boundary for a one-dimensional SVM?
A point.
A point, because in 2 dimensions it's a line, in 1 dimension it's a point, in 3 dimensions it would be a plane. And where should that point go in this case? 4. So what's the equation for our decision boundary?
X equals 4.
X equals 4. So that's it, 4. How many support vectors do we have?
2.
2. Which points?
E.
B and C. So we'll circle B and C. And then what would be the equation for the positive gutter?
Less than or equal to 4. Or just less than 4.
Well, what is a gutter?
Oh, sorry.
Equals 2.
So that's the equation for classifying points, almost. Yeah, so x equals 2 would be the positive gutter. And if we were to draw that, we would really want to draw it as something like a dashed point, but that doesn't really work, so we could do something like that. And the other gutter would be over here at x equals 6. So now if we want to calculate the value for W and B, how would we go about doing that? So first we would want to rewrite this equation as some vector W dotted with some vector X plus a constant B is equal to 0. How many components are in the vector W?
1.
1, because we're only in 1 dimension. So now instead of x and y, we just have the x-axis plus some constant equals 0. So if that's our equation, x equals 4, we could rewrite that as 1 times x minus 4 equals 0. So what would be W? 1, and then B is negative 4. So are those our final values for W and B?
No.
What else do we need to do?
Scale it.
Yeah, we have to scale it, because we could just as well have multiplied through this whole thing by any random constant. So let's say we'll use the point B to scale it. This is using the gutter constraint method. The gutter constraint says that any point that's on the gutter should have positiveness as W dot x plus B value of +1 if it's a positive point or -1 if it's a negative point. so for B, we'll have W dotted with the coordinates of B plus our little b value is -4 equals the classification of B. So what are the coordinates of point B?
2.
2. It only has one coordinate. And what do we want the classification to be?
Plus 1.
Plus 1. So this equation doesn't currently work, so we'll multiply by some constant little c. What's the left side equal to?
-2.
-2c. So if we solve for c, we get c equals -1/2. And then we can use that to scale w and b, so we get our final w value is the one-dimensional vector -1/2, and b will be 2. So we can check this using the margin width, because we have the equation margin width is equal to 2 over the norm of w. So what is the margin width in this case? Looking at that picture. 4, because it's the distance from one gutter to the other gutter, so that's 4. And what's the length of the vector w? 1/2. So 4 is equal to 1/2, so that's good. And then the other thing that should be true is w should point toward the positive points. So if w is the vector -1/2, then that means w looks like that. So it's pointing toward the positive side, so that looks good also. So it seems like we have good values for w and b. So now how do we go about calculating the supportiveness values? Do we have any equations for that? So we have two equations for that. We have equation 4 from last time, which said that the sum of the positive alphas is equal to the sum of the negative alphas. So in this case, alpha b equals alpha c. And then equation 5 said that the vector w is equal to the sum over the alpha values times their classifications times their coordinates, which in this case would be alpha b times the coordinates of b, which is 2, minus alpha c times the coordinate of c, which is 6. And we know that w is -1/2. So if we do some algebra and plug in alpha b equals alpha c, we get -1/2 equals -4 alpha b. So alpha b equals 1/8. And alpha c is 1/8. What about alpha a? 0, because it's not a support vector. Alpha a is 0. So that's basically the same as the process we followed last week for 2D SVM, except that in this case, everything was just one-dimensional. Any questions on that? Yeah.
Is there like a relationship between B and the size of like the margin?
Yeah, so B, I think, no, so B is only an offset value, so if you change the value B, it's easier to see in 2 dimensions. If you change B, it'll just move the boundary and gutters together and along that direction, so parallel to where they currently are. So only W is going to determine the margin width and the direction. B just determines basically the y-intercept. Yeah, but W determines how wide the margin is and what direction the boundary points. Other questions? More on neural nets? More on SVMs?
Oh, just for, so when we write W, should we always put it in brackets?
Yeah, W is a vector, so that's why it's in brackets. It's more obvious when it's more than one dimension, but yeah. We can take a look at another of these problems. We want to do back prop or forward, more forward and all that stuff? Who wants to do back prop? Who wants to do the other one? Okay. Okay, so let's look at 2015 final back propagation. Okay, so what weight are we trying to update? Oh, I guess it's not very clear on here. The weights aren't actually labeled. Weight 1 is this -1/25 on the top. So where we have 50 going into -1/25, that's weight 1. So what do we do first to update a weight? What formula do we have? So if you have the quick backprop formulas, there's a formula. In this case, we're just looking for the change in the weight. Well, so there's a formula, the new value of the weight is equal to the old value of the weight plus the change in it. But in this case, we're asked to find W1 new minus W1 old, so that's just the change in W1 is what we're looking for. So to get that, we're going to do the rate constant times the output of the thing going into the weight. So what would be that output? We call that out A if this is A, times delta B. So what is out A in this case? Is A an input or a neuron? Input. So what's the value of an input? Yeah, in this case it's just 50. And then we're given a rate constant? 1/2? Okay. And then we need to get this value delta B. So in this case, delta B is the delta value for neuron 1. So we can call that delta 1 for neuron 1. Is that neuron in the output layer?
No.
No, because this is neuron 1, and then it goes to some other neuron 2, which then goes to the output, or sorry, neuron 3. Okay, so that means that we need to use the second formula for if it's not in the output layer. So we get the output of 1 times 1 minus the output of 1 times the sum over all of the outgoing neurons. So who are the outgoing neurons?
Just 3.
Just 3 in this case. So we're going to sum over 3, and we'll do the weight from 1 to 3 times the delta value for 3. So what's the output of neuron 1? 4? Where does that come from? Oh, so that's the weight coming out of neuron 1. So that's going to be this weight going from 1 to 3.
So this should be 1?
Well, so what are we given?
Sorry, 1/2.
Yeah, on the diagram we're given output of 1 is 1/2. So that has to be either calculated or given. So this is 1 minus 1/2. And then we need this value delta 3. Is neuron 3 in the output layer?
Yes.
Yeah. So that's going to be the output of 3 times 1 minus the output of 3 times the desired output minus the actual output. So what's the output of 3? 1/2. The reason why we're getting 1/2 is this is a sigmoid function. Then we have 1 minus 1/2. And what's the desired output?
1.
1. What's the actual output?
1/2.
1/2. So that's the same as out 3. So now if we multiply all these together, we get 1/8. And we can plug that in for delta 3. And then we can plug delta 1 in up here and we'll get some value which comes out to 25/8. How would this have changed if we had, say, another neuron 4 there, and these both went to some neuron 5 which went to the final output? What would we have done differently?
So, we would calculate D1.
Yeah, so we would calculate D1 differently. We would be summing over neuron 3 and neuron 4. So we would do this plus the weight going from 1 to 4 times the delta value 4. Would this have affected how we calculate delta 3?
Because it's not an outgoing neuron.
Yeah, exactly. So in this new neural net, neuron 3 is no longer in the final layer, so this would have also changed. So basically, the more layers you have, the more of these deltas you calculate and plug back in. Questions on that? Yeah.
On the quiz, will we be given the equations? Or,
You should probably bring the equations. They
okay.
might be useful. I think last year they were not listed on the quiz. Other questions? Okay, yeah.
Why didn't we have to calculate delta 2?
Delta 2, because for backpropagation we only care about what's downstream of that neuron. So if we were updating one of the other weights, like the weight related to neuron 2, then we would have had to calculate that.
Okay.
Or if neuron 1 went into neuron 2, then we would need it.
Okay.
So yeah, in general, in backpropagation, you would have to calculate all the deltas, but if you're only updating one weight, then you don't need all of them.